Okay, let's see what happens when we take one water molecule, H2O, and you put it with another water molecule, H2O, liquid. What happens here? What should the, you know, um, product be? So you're thinking, okay, if you have one mole of water molecule and add it to another mole of water molecules, I'm going to get 2 moles of water, okay? You're correct, but however, to a very small extent, it's actually going to self-ionize. In other words, it's going to auto-ionize, and this is where you're going to say water molecules tend to carry out something called auto-ionization. Okay, and when they do that, one of it's going to act as an acid, and the other one's going to act as a base. Okay, so from last time, like I said, water can act as an acid and a base, and you call this amphiprotic. Okay, so when they do that, I'm going to put reversible. It's gonna one of it's going to be it's going to form an OH minus molecule, which you call the hydroxide. Okay, remember, how does it work? Since this water molecule, it's going to donate that proton or the H plus according to Bronsted and Lowry. It's going to form the OH minus. Okay, and that base, it's going to accept that proton, make it H3O positive, and you're going to call this your hydronium ion. Okay, according to Bronsted and Lowry. So here it is. There. Okay, so now let's say this right here is at 25 degrees Celsius, because temperature has a huge plays a huge factor in calculating the concentration OH and H3O positive. Okay, so for the next part, what we're going to do is we're going to try to figure out what's the concentration for both of these guys, your OH minus and your H3O positive. Okay, so I'm going to set up my equilibrium constant, which I'm going to say Kc. C is your concentration. Okay, so I'm gonna set it equal to my products over my reactants. Okay, and before we do that, you got to make sure the equation is balanced. And by looking at it, it is balanced. Okay, so my products on the right side, concentration OH minus your hydroxide times the concentration of your H3O positive, which is for your hydronium ion. Okay, over your reactants. But however, I'm not going to include my H2O liquid because for liquids and solids, you don't want to include that into your expression because they're considered constants. Okay. Okay. Next, here it is. So here's my expression. Instead of Kc, I'm going to change it to Kw this time. Okay. Kw represents my. I'll write this for you guys. Ion. Here, put this ion. Product constant for water. Okay, which is equal to OH minus times your hydronium ion. Okay, so by the way, you can substitute. You can write it as either H2O positive or you want H plus. Okay, so either way it works out too. Okay, okay, based on experimental value. Okay, the ion product constant is going to be 1.0 times 10 to the negative 14, which is very, 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 very small at 25 degrees Celsius. Okay, so again, temperature is important. If it's not 25 degrees Celsius, then that constant is not going to be 1.0 times 10 to the negative 14. Okay, so just for any particular problem, if I don't indicate temperature, you're just going to assume it's going to be at room temperature, which is 25 degrees Celsius. Okay. So last thing is, wait a minute. If we know the constant or the product constant is 1.0 times 10 to the negative 14, then what's the concentration for the OH minus and the H plus? Okay. So if OH is equal to the concentration of your H plus, and we know that the ion product constant is 1.0 times 10 to the negative 14, then that means the concentration of OH minus is equal to what? 1 point, again, you could probably use a calculator to figure this out. If not, you can probably do this in your head. 1.0 times 10 to the negative 17 molar, and that means your H plus concentration also 1.0 times 10 to the negative 17 molar. Okay, so this is where I'm going to stop, and we're gonna continue this next time by using this to understand how to calculate pH of a solution.